Okay, we're going to do some definitions. This is section 1.1 from the Zill textbook. This is part of chapter 1, or actually most of chapter 1 from the Schwam's outline. First off, definition: a differential equation, which we'll always call a DE from now on, is any equation that has derivatives in it. You can have one or more dependent variables, or even one or more independent variables. So here are some examples of DEs. Sometimes we'll use Leibniz notation, the dy dx kind of notation, or also called differential notation. Sometimes we'll use prime notation. Particularly, I don't like prime notation that much, even though it is easier to write. We will write it quite a bit. The problem with prime notation is it's not obvious what your independent variable is. When you took Calc 1, anytime you saw prime, you probably thought derivative with respect to x. But it may not be. A lot of times you have to use context clues to figure that out. But usually if you have x's and y's and you have a y prime, then that's equivalent to saying derivative of y with respect to x. Sometimes we'll use dot notation. This is from physics. So x dot here means the derivative of x with respect to time. So our independent variable here is t, and our dependent is y. Sometimes we'll have one independent variable, t, and two different dependent variables. So maybe x and y both depend on t. Sometimes we'll have partial derivatives. This will be an example of a partial differential equation. So these are all DEs because they're equations that have derivatives someplace in them. An ordinary differential equation only has ordinary derivatives, no partial derivatives. So these are all ordinary DEs, ODEs, except this one. Number 4 is a partial derivative, or a PDE, partial differential equation. The order of a DE is the highest order of derivative that we have any place in here. So this first one is a first order differential equation because our highest derivative is the first derivative of y here. Number 2 is a second order DE because our highest derivative is the second derivative of y with respect to x. Number 6 here is a second order DE. And you're like, but there's a cube. No, that cube is a power on this derivative. This is the second derivative cubed. The highest derivative we have here is 2. This is a second order differential equation. We say a DE, or usually an ordinary DE, but it could be partials also, is linear if your dependent variable never has any nonlinear function that it's in. So a linear DE, all your y's, your y primes, your y double primes, all your derivatives of y are only to the first power. No signs of y, no e to the y, no nonlinear versions of your dependent variable. So in this first example, our dependent variable is y. I've got a y prime and I've got a y. Those are both linear in y. Sure, cosine of x is nonlinear, but I can have nonlinear versions of the independent variable. This is fine. This is a linear differential equation. The second one's nonlinear because I've got an e to the y. That's nonlinear. 3 would be linear. We only have one version of our dependent variable x, and it's just x prime or x dot to the first power. 5 would be nonlinear because I've got a cosine of y. My dependent variables here are x and y, I've got an e to the x, that's nonlinear. A cosine of y, that's nonlinear. Number 6 is nonlinear. Not because of the x squared. I don't care what the x does. X is independent here. I've got a y double prime cubed. I can't have any powers on my y's or my y primes or any version of y. This is nonlinear. Number 7 is linear because look at all the y's. Y to the first, y prime to the first, y double prime to the first. I can have nonlinear versions of x because it's independent, but the dependent variable is all linear. Another way of expressing that is we can rewrite, if we wanted to, we call this normal form. But when we move everything to one side, we call this normal form. We can express the dE as all of my different derivatives with some function of only x in front of them. So whatever is going on in front of each one of the derivatives only depends on x. We call these our coefficient functions, and they only depend on the independent variable. And we call it normal form if we take this equation and solve for this highest derivative, get everything to the other side, and divide through by this coefficient function. We say a function is a solution to an ODE on some interval if that function, it has to have a bunch of derivatives. If my order of my differential equation is n, then my function better have n derivatives, otherwise y in the nth derivative doesn't make any sense. We need all those to also be continuous on that interval, and that function satisfies the dE. Okay, so this is important. Back in algebra, when you're solving for x, you're getting a number. You get x equals 3 and you're done. Here, solving a differential equation, you're not trying to get a number. Your goal is to find a function that satisfies the differential equation. So our answer will be an entire function, y equals some function of x, or whatever our variables are. Typically, most DEs have more than one solution. They typically have an infinite number or an entire family of solutions that will all work. Most DEs can be written in one of two different forms, or they can all be written in one of two different forms. A lot of times we get lucky and we can write our solution as an explicit function. Y is some function of x. Sometimes that's not possible, and our solution will just be a curve. It doesn't pass the vertical line test. It's not a function in the strict sense. It's just some curve that it's a relationship between y and x, and we'll have an implicit solution instead of an explicit solution.